Shall we wait a bit? There are about 20, I think 20 participants. Shall we wait a few minutes?
Yeah, Mr. Chairman, you decide.
About 5 minutes, we wait and then we will start.
Okay.
All right, thank you. Hello, can you hear me?
Yes, Prof.
Yeah, Professor Tenalam, Professor Seifu.
Okay.
So shall we start?
So we may start.
I will briefly introduce the moderator.
My name is Tenalam from Addis Ababa University. I'm going to moderate this session. So good afternoon. Good wherever you are. All participants, you are welcome to this webinar. We will start with a short introduction of Professor Seifu, and then I will leave the session to the presenter, Professor Seifu Kebede. Professor Seifu Kebede Gurmessa is a hydrogeologist by training with a specialty in tracer hydrology. He obtained PhD from the University of Avignon, France in 2005. He has served in Addis Ababa University as associate professor in the department, the School of Earth Sciences. He joined the University of KwaZulu-Natal as associate professor of hydrology in 2009. He is a member of the Center for Water Resources Research of the university. He published more than 50 peer-reviewed articles in reputable journals and one book. He is the Sub-Saharan Africa Vice President for the International Association of Hydrogeologists. He co-chairs the Water Quality Commission of the International Association of Hydrogeologists. He is a member of the Friends of Groundwater Network. Earlier in his career, he served the International Atomic Energy Agency as a junior professional officer and UNESCO Addis Ababa office as water program coordinator. Today, Professor Seifu is going to present a very important issue of hydrology His presentation will be more on tracer hydrology. So the title is, where is your tap water coming from? Does it matter? Mapping water scarcity risks using isotope tracers. This is the topic that you are going to hear. Welcome, everyone. Now I'm going to leave the session to Professor Seifu. Welcome, Professor Seifu.
Thank you, Prof. Denalem, and thank you, Dr. Fallaka, for inviting me to present this talk. And as you rightly said, it is about method development for tracing water sources to taps, where is water in a tap coming from, and different tools, tracer tools that we have that has been developed to trace the tap back to its sources. And I'm based at the University of KwaZulu-Natal Center for Water Resources Research, and I joined the university in 2019. And contributions to this presentation, other contributors to this presentation are Bahailu Burhanu and Kebede. And this study has been sponsored, financed by the International Atomic Energy Agency and by REACH program. And yeah, these are the two main sponsors of this study. First, I would give you some highlights about the state of the problem, what is the problem there, and why the isotope tracing tool was necessary and required. So Addis Ababa is a rapidly growing city. Although this is about Addis Ababa, the case may be applied in any other cities in developing nations with complex urban water infrastructure and with urban areas facing water scarcity. And Addis Ababa is a rapidly growing city, a mega city. Reported population, official population is around 5 million. And Addis Ababa gets most of its water currently, as it stands now, from groundwater, about 67%. And the remaining water is sourced from surface waters. And Addis Ababa is located in a relatively humid area with rainfall amount of 1,200 and potential evaporation of 1,500, mean annual temperature around 17 degrees Celsius, and 2,000. This is the highest elevation area in city in the world, 2,400 meters above sea level, and underlain by volcanics. And as you can see here, the city has grown very rapidly. The gray area here is in 1970s, and the yellow area is in year 1990s, and the red areas and the orange areas are built up areas in 2000 and 2050 respectively. So the city is rapidly growing, and yeah, that is what the city looks like now. Okay, around 600, 700 kilometers square. And so Addis Ababa is water constrained. So about 1 million meter cube per day water production is required to meet the needs for the town, for the city. But currently the city municipality produces half of it. And there are several areas or sectors needing water, like newly rising buildings, the slum areas, industries, and the newly built up condominium houses, and all this competing for water sources. And then in this competition and underwater scarcity, there is a group of stakeholders or users who are at risk. And then who is at risk? In most instances where we analyze water security risk at urban scale or for urban areas, we tend to see the entire urban area. So when you see the entire urban area and see how much water is produced and how much water is required, we will have some indications about the level of water security risks. But household level, what is the risk of water scarcity at household level is rarely investigated or rarely analyzed. And the purpose of this isotope tracing work is by mapping or by trying to map the source of water in your tap, will it be possible to see the risk that you will face, individuals or dwellers would face in the future, call it pollution, call it water depletion, etc. So when you see in detail the sourcing for water for Addis, so this is Addis Ababa, there are two major reservoirs, the Gurmessa Dam, the Kebede Dam, and there are distributed or scattered wells and springs within the city, accounting for really substantial volume of water sourcing the city of Addis Ababa. And there is also another well field in southern part of Addis. And then the water comes from these four principal sources, but there are a number of other details. If you see in detail, for instance, the Akaki well field, there are multiple well fields, shallow, tapping into the shallow sources, tapping into the deeper sources. There are several well fields in southern part of Addis, some of them under construction, and also in eastern part of Addis, there are well fields under construction. And then water production only covers nearly 60% of the demand, and there are multiple sources. And then these multiple sourcing adds complexity, particularly to water quality monitoring. All these water sources have their own risks and water quality issues, and then it adds some complexity. We'll see this later during my case presentation. And then most of the water distribution systems are connected beneath residents' houses, particularly in this District 1, District 8. These are the old part of the city. The pipe networks are underneath the houses and difficult to access. And then in some instances, you don't know where the pipe is sourced or sourcing its water from. Is it from the Kebede, or is it Gurmessa, or is it from Akaki? The dwellers, they don't know it. And even the city administration at some stage had been struggling to spot from where the pipe water is connected to, from which source the pipe water is taking its water from. So the city administration at some stage, the water utility at some stage has hired consultants to map the pipe network in Addis Ababa by also hiring retired people to come on board and identify which pipe is connected to which. So it's a very complex pipe network. And then in this situation, it was difficult really to know where the water is coming from. And then there are different stresses on these water sources. If you see in detail, the surface water sources, there are seasonality problems. Dry season, wet season, water availability is not the same. And pollution is another problem with these sources, and siltation of the reservoirs. And when you see into the shallow or the boreholes within the urban areas and the springs within the urban areas, pollution is being felt, and in the deep reservoirs are okay from the perspective of pollution, but mining of the aquifer, because some of these deeper aquifers are not connected to present-day recharge, and then pumping is leading to depletion of the resources. So different sources and different stresses: climatic, environmental, and aging of infrastructure. In particularly in older part of the city, leakage is a main problem. Infiltration to pipes when there is water interruption. Any environmental pollutant from the environment infiltrates into the tap water and changes the water quality of the pipes. And reverse flows from temporary household level, reservoirs, water flows back into, this is not uncommon, flows back into the pipe network. So any changes in water quality within households will eventually go back to the pipe network and then affect the water quality. So there are additional factors or risks, like whenever a geographic environment gets its water from another geographic environment, there may be from another administrative boundaries, there may be some political risks as well. This is not the case, the only case for Addis Ababa, but many towns face that kind of problem, boundary. So where do you put the boundary of an urban area? Okay, the physical boundary, if you demarcate it, still people live outside that boundary. And then which one do you consider as urban and which one should get the service, etc. So the definition of urban in terms of service delivery is challenging. So the motivation for this work are the following. Number one, to map by mapping where tap water comes at household level using tracers, then is to map water security risks at domestic level. And secondly, is water quality change, is to map water quality changes within the pipe network. Actually, this presentation was, the motivation for this presentation was another presentation that has been made at the Water Center. I think it was webinar number 4, whereby there has been a study of water quality changes within the pipe. And then in complex pipe network, like what you see in Addis Ababa, it may be necessary to first distinguish what causes the water quality changes between the tap water and its source. Maybe it is something changes within the pipe itself, or because of infiltration of contaminated substances or water from the environment, or it can be that the urban utility is injecting or adding water from local sources, connect the groundwater sources into existing pipe network, and then the water quality that you measure in the taps doesn't necessarily represent the water quality of the reservoirs, the major reservoirs you see in the southern, eastern, and western part of the town. So by tracer study, the attempt or the motivation was, is it possible to use tracers to identify from where the water is coming so that we inform the water quality studies in the pipe networks as the reason as to why water quality changes within the pipe network. So that was the motivation, the other motivation here. And then informing policies and practices, in terms of, for instance, water quality monitoring. There are guidelines that the city administration is using, but from the observations that we have in the city, what kind of monitoring is required. So to cope up with the challenges of water scarcity, these are the different measures the municipality is implementing, like shifting to large-scale groundwater sources. Initially, the city used to get, I'll go back to one slide here. These are, for instance, in 1940s and 1960s, the city was sourced from Gurmessa Reservoir. So the Gurmessa Reservoir expanded gradually, adding new small dams to supplement the dam. So it started in 1940s and completed in 1967. And then as the demand increased, so the city has to also get other sources. Like in 1970s, they started the Legadadi Reservoir, the Ray Reservoir. So the sourcing has been shifting, starting way from 1901, when the railway station was supplied by a spring source piped to the railway station from a place called Wajaja. And since that time, the sourcing of water to the city has been changing. And then all these adds complexities to the pipe network and from where the water is coming to the city. So to cope up with these challenges, there has been a large shift, policy shift toward this, encouraging groundwater resources development. And it is also assumed that groundwater is more resilient to climate than surface water sources. And then decentralized pocket area self-supply. The government or the city administration is encouraging self-supply, particularly large institutions like universities, hospitals, and some industries located within the city to drill their own borehole and then source their water needs. And also those condominium houses, some of them are sourced from local boreholes. And then water reservoirs at household level. This is what you see in practice, particularly among well-off households. Those white patches, you see here dots, you see on the roofs here. These are reservoirs of approximately 2 meter cube to 5 meter cube water. And then those households hold water for the day when they will encounter water cut. So there are a number of thousands and thousands of these. If you fly over Addis, you remark what I mean. Many households holding water in those reservoirs. So the implication for this for water quality and for other, I'll see what the isotope studies have told us about these water reservoirs. And water rationing and water tracking are the other policy measures and practices being taken. And then, so what is the risk associated? So is it like by doing this, have we reduced the risk or we encountered new risks, particularly related to water quality? We'll see that. Those 3 objectives: characterizing the water sources, meaning the reservoirs, which are located here and there, and the borehole, the aquifers from which the boreholes tap their water. What is the risk on these water resources? So using isotope tools, one can tell, whether these waters are resilient, these groundwaters are resilient or less resilient. And then tracing the origin of the tap water for household level risk mapping and inform water quality monitoring. These are the 3 objectives. So 2 passing remarks now. One is about the WHO guidelines that the Addis Ababa City Administration is using for water quality monitoring. Like for every 5,000 people, the water supply has to be monitored, like 1 sample per month. So if a water source is supplying 5,000 people, at least you need 1 water sample to be analyzed per month to monitor the water quality issues. And then this is a guideline. So if 5,000 to 10,000, 100,000 means you need about 100 water samples. And then this is the WHO guidelines that the city administration is currently using. And this is a publication, an MSc thesis by someone called Mokanin, showing that he studied the water quality changes within the pipe network. And this is the source reservoir at the 0. So the study was E. coli. E. coli as the reservoir was 0. And Warada 8, this is a district in Bole subcity, showing some sign of E. coli contamination. And Warada 6, you see a number of tap waters showing high E. coli, and some of them even very, very high level of E. coli. And then another region, a regional study in Addis, shows even many E. coli counts in the tap water. So the problem now is, what causes this E. coli contamination? Is it because of infiltration of contaminated environment into the pipe network, particularly during negative pressure development within the pipe following water interruption? Or is it related to injection of groundwaters which are contaminated, okay, and which contain E. coli and injected into the pipe network? Or is it E. coli that develops within the pipe network? This is also possible. If you have trace amount of E. coli at the source that has not been treated, then gradually this E. coli can culture and develop within the pipe network. So that is when you need, what is the source of this water in the tap water is. So that is now, can tracers be used to identify where the water is coming from and whether that water quality changes is because of infiltration or addition of groundwater into into the pipe network intentionally because of to boost water supply sources. So now I'll give you some highlight about the studies that has been conducted in the city of Addis Ababa. So 3 tracers have been measured: electrical conductivity, oxygen 18, and hydrogen. I'll tell you what these are for non-experts in isotope hydrology, what this means, and radon 222. These 3 tracers have been used. When we say tracers, we haven't added anything into the pipe network. These are naturally occurring materials or substances. Electroconductivity, okay, I'll discuss them one by one. So electroconductivity is a reflection of the proportion of dissolved solids that you have in waters. So if you have higher dissolved solids, electroconductivity of the water is high. And then if you have lower total dissolved solid ions, the electroconductivity is low. Generally speaking, groundwaters have higher electroconductivity than surface waters because groundwaters tends to stay longer time in the environment and then acquire ions from the rocks and from the soils. And shallow groundwaters generally have higher electroconductivity compared to the deeper groundwaters. And then electroconductivity is like index parameters. Whenever electroconductivity changes, we suspect there is also other change in other ions, change in microbial contamination, change in contaminants, and change in other parameters. So it is kind of very simple to measure and very easy to measure, and the equipments are not also sophisticated. A simple handheld electroconductivity meter can be used to detect the level of electroconductivity in waters. And the other tracers that has been employed are, here is oxygen 18 isotope, a water molecule, H2O. So the O in your water, that O can be oxygen 18 or oxygen 16. Predominantly it is oxygen 16, but there are some oxygen 18 also. So the ratio of oxygen 18 to oxygen 16 is a very good tracer of water movement. Once a water acquires a particular ratio, oxygen 18 to oxygen 16 ratio, that ratio will not change, for instance, within the pipe. If the water is moving from within the pipe, that ratio will not change. It only changes where there is phase change, when water evaporates or condenses or sublimation. During this phase change, the isotope ratio may change. Otherwise, because of chemical reactions, etc., this ratio, oxygen 18 to oxygen 16 ratio, doesn't change. So if you inject water of a particular composition at a reservoir, let's say a Kebede reservoir, at the end of the pipe, you will get the same isotope ratio, or you should get the same isotope ratio, because in the pipe network, you don't have evaporation, you don't have any form of condensation within the pipe. So the ratio will remain the same. So that is why we make use of isotopes of water, which we call them conservative tracers. So these are good indicators as to where the water is coming from. And the other tracer, very interesting tracer, I would say that this is the first of its kind that we used elsewhere, radon 222, to trace source of water in pipe networks. I haven't come across any literature on the use of radon 222 to trace source of water in pipe network, and also to determine residence time. It's a very good tracer because radon is a gas, heavy gas. It is radioactive. Its half-life is 3.82 days. This means once radon goes into the pipe, it will naturally decay within the pipe, and half of your radioactivity or half of the substance will decay within 3.82 days. So it has very short half-life, and it can be therefore a good tracer to determine for how long water stays in or stayed in the pipe network. So this is a preliminary study that we have conducted, and this was actually also one of the motivations to present the results here, to support the presentations that has been made during webinar number 4, radon 222. I'll show you the results soon. So before starting the tracer sampling and measurement, what we have conducted was kind of snapshot water interruption studies. This was meant actually to design our sampling strategy. So we took randomly 20 sites, 5 surface water sourced, 5 groundwater sourced, and 5 mixed surface water groundwater sourced sites within Addis Ababa, and monitored water interruption for a period of about 10 days during wet season and dry season. So black means water cut, blue and green means water is there. Water is flowing, blue during daytime and green during nighttime. When you see here, comparing surface water and groundwater, mixed groundwater surface water sourced areas encounter more interruption, both during dry season and during wet season. And during dry seasons, surface water sourced areas tend to encounter more interruptions, and the groundwater sourced areas cope during the dry season. But in wet season, you have more interruption in the groundwater sourced areas, and this is also related to electricity supply, etc. So shifting to groundwater sources did not improve service level, again, as attribution that it is a resilient source. Although groundwater is oftentimes seen among us, among hydrogeologists, that it is a resilient source in urban water supply, that resilience may not end in resilience of your tap water, flowing tap water, at household level, because it all depends on how the pipe networks are interconnected, the aging of the pipe networks, electricity supply, and then if there is a power cut, it takes time until a borehole is maintained, etc. But now I'll show you the tracer studies, the results from the tracer studies. So one of the things that has been done is a 24 hours monitoring, hourly monitoring for about 1 week of electrical conductivity of the pipe waters at many locations, I think 4 or 5 locations. I'll share you 4 of them now. So the electrical conductivity value, number 1, this is at a site called the British Embassy, around British Embassy. So it shows this fluctuation, daily fluctuation. Okay, maybe this daily fluctuation reflects, number 1, temperature variation within the pipes. At the same time, it also reflects water use, probably. So the highest water use is in the morning and in the evenings. And during mornings and evenings, you have lower electrical conductivity. So that is when the water is flowing, not stagnating within the pipes. And during the daytime, you have increasing electrical conductivity. Maybe this is related to some stagnation within the pipe network. And then you have higher electrical conductivity during the daytime. So you have this daily variation in the electrical conductivity, and therefore also possibly other parameters will change along with electrical conductivity. And then on this day here, around the 27th or 26th of May, suddenly the water electrical conductivity increased. And then we don't know the reason for that, why this has increased. So this is all to say, if you go out to the pipe water and collect your pipe water and measure its microbial contamination or whatever, a snapshot data may not be telling you what is really happening in pipe networks like in Addis Ababa, because of these variations in diurnal variations and sometimes unknown causes or change in water quality because of unknown causes. And this is a borehole source showing some uniform electrical conductivity values, but jumped and dropped at 2:30 p.m. and then recovered later on. And probably this is related to stoppage of pumping and restart of the pump during the, when the people are not using. This is a condominium house from a condominium state area. So that drop may be related to stoppage of pumping and then during the stoppage of pumping and restart of the pump, a new water quality, because now the water is coming from the shallower depths. So it will have another electroconductivity values. And then the most interesting one, this one also, is whereby this is a borehole source monitored from May 4 to May 8. And during May 4 to May 5, it shows high electroconductivity value. But on May 6 and 7, this is 2020, there has been water cut. Borehole was not pumping. And then when the water returns on this date here, May 8, it returns with a different electroconductivity value. So this shift in water quality during water interruption, so we are measuring only the index here, may be related to the borehole pumping from different level now, bringing the water from different level. Initially from deeper level, as it was pumping for continuously, but stops and recovers, the borehole recovers, and then pump again with a different water quality. So any one-time water quality measurement will not give us sufficient information about water quality changes within the pipe network. And this is another site. This is a place called, actually this one is Kebede, for those of you in Addis. This one is Jomo, Kebede, and this one is around Faransai Legation. You see here at 5:30 p.m., electroconductivity of 110 gradually decreased, okay, until the 8:30 p.m. and then increased again. And probably this is because of that site getting its water from two sources: a reservoir coming from the big urban water supply source, and a spring source which is added into the system. So two end members supplying the same household during different time of the day. So these are kind of 24 hours monitoring for a certain period of time. And this data shows us there is substantial variation within the pipe network diurnally, and any one-time measurement is not may not give us a full picture of the water quality in the pipe network. The other study was a snapshot survey of electroconductivity of about 510 water taps from Addis Ababa. And then you see this extrapolation to show the electroconductivity levels. Red means higher electroconductivity and green means lower electroconductivity of tap waters. When you see like this, the red areas show high electroconductivity. These are groundwater sourced areas, principally groundwater sourced areas. And the green are principally the reservoir sourced areas. But in some places you have, yellowish, like here where you have a mixed surface water and groundwater sources in those areas. So, and then if you see this map, electroconductivity map, along with the supply sources that the city administration or the urban water utility tells us, you see some very good correlation. So where they say this part is getting its water from groundwater sources, we observe high electroconductivity values in the tap waters, and the blue areas are surface waters, but not entirely surface waters, because there are groundwater sourced areas when you see the electroconductivity values. Although the city administration says this is surface water sourced areas, we observed groundwater inputs into the pipe network in this area. So this is to say, simple tools like electroconductivity can tell you where your water is coming from. And the survey of oxygen 18 isotope ratio also mirrors the electroconductivity, and then can inform or can tell you where your water is coming from. For instance, the green area is more negative value, that has its own meaning, isotopically depleted values. These isotopically depleted values come from deep groundwater sources. So this area gets its water from deep groundwater sources. So the risk for this area actually is mining of the aquifers at the source. So the source is somewhere here outside the boundary. The deeper aquifers from Agag well field supplies this region. And then whatever happens, on the Agag well field will impact this pipe network in this region. And then you see here, reddish area, which has not been picked by the electrical conductivity, but picked by the oxygen isotopic content here, isotopically enriched. And this enrichment tells this region may be sourced or is sourced from the shallow groundwaters. Shallow groundwaters are generally enriched in their isotopic content compared to the deeper ones. So this is the shallow groundwater sourced area, deep groundwater sourced area, surface water sourced area, and groundwater sourced area. So the oxygen 18 can, and deuterium equivalently, can tell you where the water is coming from in your pipe network. And then the radon has been used for two purposes. The first purpose is to tell where the tap water is coming from in terms of groundwater and surface water. And secondly, to determine the residence time, how long the pipe water stays within the pipe after it is injection into the pipe. So first, when you look into the numbers, small numbers here. So I haven't told you about the details about radon. Radon is produced inside rocks. So groundwaters generally, in most environments, in volcanics, in granites, in even sedimentary rocks like sandstones, contain high level of radon gas, because radon comes from uranium decay. So uranium releases radon gas. And this radon gas exists in groundwater. But sooner the groundwater discharges into the surface, and runoff or rainfall that produces runoff will not have radon, or there's very trace amount of radon because it degases or decomposes by radioactivity. So groundwater has high radon content compared to surface waters. So what you see in this map is some measurable levels of radon in groundwater sourced areas and below detection limit. Actually, the detection limit of our equipment, DRIDGE RAD7 electrochemical counter is 37. So all area here in red shows less than 37. So most of the radon is encountered in this environment. And we took a transect on a single day, starting from a source to here, and these three samples were taken on a single day. And then you see a progressive decline from 202 becquerel per meter cube to 143 becquerel per meter cube to 112 becquerel per meter cube. So this progressive decline shows the aging of water within the pipe. So we calculated like 0.75 days, less than a day, 0.75 days, or about how much would that be? 18 hours, about 18 hours for the water to come from this source to that source. So we are still testing this, the radon tool to determine the age, but you can see in terms of telling where the water is coming from, it is proven to be a very useful isotope. And then the other snapshot study was about the impact of these household level reservoirs. Okay, the reservoir. So what has been done is compare the isotopic oxygen 18 to deuterium isotope ratio of water, tap water, before the household and after, sorry, before the tap goes into the household and after it passed through the reservoir. So this is before the reservoir and that one is after the reservoir. So before the reservoir, it is depleted, and after the reservoir, it shows a different isotopic composition. So this change in isotopic composition in those small reservoirs is an indication of evaporative water loss. How much of water is lost? Not yet calculated, we haven't calculated, but you see in almost all the places that we have sampled, we see that there is evaporative water loss within these reservoirs. So this has an implication because most of these households are well-off households storing water, and also some water quality changes can happen within these households and flow back into the pipe networks. So yeah, there are some issues that the isotope tracers can tell us about what happens within these reservoirs. Sorry. And then a quick study also on the sources with respect to the emerging contaminants. So tap waters sourced from decentralized wells within the town. Okay, decentralized wells, and most of them are relatively shallow, and you see high level of emerging contaminants in those tap waters sourced from boreholes located within the city. You see things like DET, caffeine, atrazine, etc. And in these tap waters, you get even cocaine, ibuprofen, and paracetamol, these kind of compounds in those borehole sourced pipe waters. And in old well field, this is the old well field in Akaki, which is a shallow reservoir, shallow aquifer. You see also high level of emerging contaminants. And in the deeper borehole, you don't see high counts of emerging contaminants. In Arba runoff, of course, obviously you have a very high level of emerging contaminants. In surface water reservoirs, it is fine because the surface water reservoirs are relatively located outside the town where most of the pollution is happening. But in the old aquifers, which are shallow, and in the aquifers within the town, this is not sampled from the aquifers. This is sampled from the tap waters sourced from these different reservoirs. So you see high contamination level in areas that are sourced from shallow well fields and boreholes located within the town. So I think I'm taking a very long time, but I would like to just very briefly highlight the part of characterizing the sources. So whatever problem happens on the source will be reflected in the pipe and at household level. So what are the different pressures on the surface water sources and on the groundwater sources? So using these isotope tracers, characterization of 2 reservoirs, a well field, and 3 deep, one shallow well field and 3 deep well fields have been kind of characterized. And one of the results is that the deep boreholes in Akaki here, you see here, tap into the regional groundwaters with different isotopic compositions compared to the shallow ones. The shallow boreholes are connected to present-day recharge, and that is why also we see high level of contamination in the shallow waters. And then in the deeper systems, they are less contaminated, but the risk of this is long-term depletion because they are not connected to present-day rainfall, which has these isotopic characteristics here. So characterizing the source and then knowing where you get your water from, then one can know, the risks that is associated with where the water is coming from. So some key messages that is drawn from this tracer survey and also related surveys or related studies are the following. On service level, TAP is only as good as the water it provides. And despite the increase in water service network and source development, the supply has increasingly become unreliable and about 55% reliability. There has been a lot of investment on groundwater, but that didn't end up in resilient taps. Okay, the source is resilient, but not the tap in many instances, regardless of all the investment that has been happening. So when you talk of conjunctive management of surface water and groundwater, it is not a panacea in urban areas, unless otherwise we plan how to distribute these sources to the dwellers. And groundwater and climate change, resilient resources doesn't end up in resilient sources at the household level, at least in Addis Ababa. That is what we see. Those areas that are sourced from groundwater also face problems. Okay, problems of interruption. Tracing water sources, so electroconductivity, radon, and water isotopes effectively distinguish between different tap water sources. Stable isotopes of water effectively trace the source of tap water, even when electroconductivity measurements are unable to discriminate between sources. And therefore, this kind of studies will have some, can be employed by people who are involved in water quality studies in pipe networks. So even when single source is attributed to source of tap water, its water quality may change over the course of the day, owing to degree of pumping, residence time of water in the pipes, mixing of water sources, water use conditions at households. NB, therefore, implication of water quality for water quality monitoring. So like for every 5,000 people, 1 sample per month, and then a snapshot sample. This will not give us sufficient information about the water quality, because water quality changes in cities like Addis Ababa. It changes diurnally with the level of pumping, with the level of where the water is coming from, and with the interruption, etc. So this water quality monitoring design needs to incorporate this situation of changing sources, changing water quality with time. So the water quality studies in pipe network must recognize the importance of water quality variation within the pipe network caused by injection of water from other sources. So water quality changes within the pipe network is not necessarily related to what is happening within the pipe, but it's also it is also impacted by external environment, and particularly by unaccounted water source that is injected into the system to boost the water availability in an environment in the city. But this kind of measures to boost water quality or water quantity has its own consequences, which is the water quality dimension, which is often overlooked. So with this, I conclude my presentation, and thank you very much.
Okay, thank you very much, Professor Seifu, for a very interesting presentation. Now, I will give the chance for the participants, if there is any question or reflection. So the floor is open for the participants. So I don't see any hand.
There is a hand.
Yeah, just I can see that.
There are many.
Okay. Maybe Dr. Fallaka, you can give the chance for them. I can't see here.
Or shall I?
Yeah, sure.
Okay, Prof, thank you very much. Professor Seifu, thank you very much for your excellent presentation. This gives us an overview about the quality of the water in Addis, what we are drinking, where it comes from, how to distinguish one from the other. It's really an excellent overview and presentation. Thank you very much for that. I just raise my hand to say hello, and say hi, but also to give some questions or some comments regarding you have used several parameters, particularly the EC. It really all gives us some ideas where where comes from. So it helps, but usually EC is affected by the temperature. As a result, we usually report EC as a standard temperature, like at 25 degrees centigrade, because it is affected by temperature. So maybe the daily variation or the diurnal variation could be associated with somehow with temperature. Otherwise, it definitely capture where the water comes from. One thing that I don't know, you know very well about this radioactive gas, but the residence time is short, as you have shown us. But within that 3 days, we drink the water. Does that have an effect on us? This is what I want to know. Thank you very much.
Okay, may I answer this one and move on to the next one? Mr. Chairman. Hello?
I'm hearing you, but...
Okay, so let me answer this one and then move to the next question. Yes, hello, Dr. Tadessa, how are you? I hope all is well in Addis. Yeah.
Thank you. Yeah.
Yeah. So you are right in this diurnal variation in electroconductivity. This could be attributed to temperature changes during the day, and some EC meters have internally inbuilt, temperature adjuster. Yeah. So EC meters with temperature probe, and you don't have to adjust what you measure. And yeah, this is not a big variation actually. This is like 10 micro. So maybe within the error of the instrument's capacity to adjust the temperature. So yeah, this could be related to it. But the main one, this one here, that we encounter day 1, 2, 3, 4, 5 on the 6th day. Yeah, just a sudden jump in electroconductivity at a place that we know is sourced from the main pipe coming from Kebede Reservoir. So it's jumped here. So we don't know what caused that jump. Is it related to because of maybe high water use on a particular day? The municipality added groundwater source mixed groundwater source into the pipe, and then that reflects addition of groundwater into the system, or we don't know why that happened. Okay. And you are right with the temperature, and with regards to the radon in the waters, actually this is very, very, very low amount to cause any health risk. It has nothing to do with health. The health level, if it is the number you see here as 200, if it was 200,000, yes, it is a health risk. But this is just 200, detectable, very trace amount, very, very trace amount of radon. So it will not have any health risk. Even in the boreholes that is supplying this tap waters, it is around 8,000 becquerel per meter cube. So that is very small amount when you assess health risk. There's no health risk at all. And then that is why even, oftentimes people in the health would report this as trace and non-detectable, or the trace, and it's not of any health significance. But when you see it from a hydrology perspective and tracing perspective, it has some power. the changes in water quality within pipe network will depend on how long the water stays in the pipe. If the water stays longer, has a longer residence time, the tendency of change is going to be high. So this radon measurement will give you an independent check on pipe residence time. It could tell the pipe water residence time and as an independent tool to determine age of water in the pipes. Okay, so yeah.
Thank you very
Okay.
much. Thank you very much.
Thank you, Talis. There is a hand by Syringe, Professor Syringe Guy.
Good morning to everyone. Good morning, Professor Seifu. Good morning for colleagues who. So this was a really interesting presentation by my colleague Seifu, and he has highlighted really very good stuff, especially using isotopes tool, stable isotope tool in radon for short residence time. So I understand well how ADIS is built on water supply system from the groundwater system to tap, and also from these different sources. So I don't know whether it will be a question or a contribution, since you are focusing mainly on tap water, and the network is quite complex because you've got some area which are fed from the old well field. Some other area are fed by the new well field, and some other also are mixing between springs and surface water, reservoir water, and groundwater as well. So I was wondering, is there any possibilities to
Hello?
Wait, sorry, I was receiving, I'm using my, you are receiving me now?
Yes.
Yeah, we can hear you. You just start from where you stopped.
Yeah, because I'm using my my telephone for this
All right, go
presentation,
ahead.
and I some call are coming in. So I was wondering if there is a possibility to track the water from and focusing in this special area like the south, where we know that it is fed from I don't know, the old well field or the new well field, to track the water from the sources and to getting to the network, distribution network, by monitoring few tap waters down to the end of the network. So we'll know whether there is, as a contribution, like leakage coming in from the sources to the networks, or even pollution, because we know that when we pump from the sources, maybe there is no microbiological pollution. And this, I suspect, as some of the results you presented, that the E. coli is coming mainly from leakage. This is my question. It's my understanding of how I see this graph. So this is my question, and so you can really monitor the characteristic of the isotopic, stable isotopic data, radon data, and EC data from the sources, and getting to the same line of network getting to the end of the network in a particular area. So I put this, it is because you are doing the same kind of work here in Dakar, tracking the water from the source down to the tap water, and even down to the reservoir water, because we know in Africa that we are facing a lot of wastewater management, because all this tap water getting to the sanitation system network are getting down to the groundwater. So, and this, there is a possibilities for getting us through very simple models using these conservative elements and this time residence parameters to see what are the input of this as a pollutant down to the tap water. This is my question or contribution, whether it's possible. Thanks.
Okay, you may reflect, Professor Seifu.
Yes, Prof. Fai asked and contributed a very nice, line of thought about monitoring, And as I've said, the study presented here is a snapshot survey, snapshot survey to design a new campaign, any work in the future. And what we are planning, for instance, now is, as you rightly said, more monitoring at shorter time interval, okay, of electroconductivity. Is happening now. We are measuring electroconductivity on hourly basis at a few locations, and then also in the pipe networks and at the source. And hourly measurement of isotopes could be very costly, but we are also doing this transect study. Take an isolated area and then start from the source until the end, and then follow the pipe network and measure the radon level, and use this to compute the residence time. The motivation is residence time of water in the pipes, because that data is an independent data to help water quality experts, to investigate what is happening within the pipe network. So we are planning, and we are doing that in that line. So this project will end by 2023, end of 2023, and then we are considering this sampling design, Professor Fai. Thank you very much for your input, nevertheless.
You are muted, Professor Tenalam. You are muted. Please unmute.
Okay, can you hear me?
Yes, we can hear you now. You are still muted. Please unmute. Okay, now it's okay.
All right, okay. I don't see anyone showing hand.
There is one question in the chat box. I think Professor Seifu can see that.
Yes,
So there is one question.
Yes, a question by Kaliso, my friend from Lesotho. Kaliso asked about this return flow. Return flow it happens in such a way that water comes to a household, and then because of pressure change within the pipe network, it flows back, and if that water is in a reservoir or in contact with unhygienic environment, that environment would contaminate the pipe system. And then infiltration into the pipe from the environment when there is power interruption, when there is water cut, negative pressure develops, and then the pipe sucks whatever it encounters in the environment, and the pipe gets contaminated. These kind of problems, with our study, we haven't seen it, but there is another study which specifically dedicate on that aspect. And then, yes, pipe network cut, water cut in pipe networks would lead to, or can lead to, a contamination of the pipe sources because of infiltration into the pipes. But we don't have direct evidence now at this stage to demonstrate that.
Any question? I don't see anyone.
I have one very short question to Professor
All right, go
Seifu.
ahead.
Well, first of all, thank you very much for this very excellent presentation. And my question is, you said you will come up with some kind of monitoring strategy by 2030. So yeah, 2023, I think.
Yes.
So my question is now, considering this complex water network and the different water sources you showed, and other many factors, so we may need actually a different monitoring strategy for the city. So yes. Is it possible to come up with some more appropriate monitoring strategy, because you even showed some kind of emerging contaminants? And
Yes.
of course, we are also doing research on emerging contaminants, so especially pharmaceuticals and other related contaminants are detected in many water points. So both the treated and untreated ones. So is it possible to design, to come up with a more appropriate monitoring strategy specifically for this kind of water supply scheme? Thank you very much.
Yeah, that is a very good question, Dr. Faleka. I think at this stage, I cannot give answers. Nevertheless, the data that we have, or the data that has been shown, leads to the need for an appropriate monitoring design for a city like Addis Ababa. For instance, following a water cut, if there is a water cut in an area, and then up on the start of, the reconnection of the water, okay, maybe you can propose measurement at certain sites following those water cut events, and then inform the communities what to do. And if there is a groundwater mixing into the system, and if that groundwater is sourced from particularly the shallow boreholes, then the frequency of sampling must increase compared to the areas which are sourced entirely from the reservoirs only. So I think from now to the end of the project time, we'll come up with certain proposals, what can be done in these complex environments. Nevertheless, these tools, the tracer tools, can inform. That is the purpose of today's presentation, can inform how to design our monitoring and increase urban water security with respect to water quality.
Okay, Professor Seifu, we really thank you for this insight.
Sorry for the interruption, Professor Tenalam. There is one inquiry in the chat box. So I think this is.
Yeah, I have seen it. I'm going to ask him this about publication. So.
Yes, exactly. Yeah. Thank you.
No, it has not been published. It has not been published, and we are considering publishing it in 2023.
All right. So far this work was not published. So I hope this interesting presentation. I mean, this piece of work will be published in reputable journal. Hopefully, we will make use of this new direction to continue the research. I think we have to wind up this webinar. The presentation shows us how simple natural tracers can be used in tracing the dynamics of surface water and groundwater in piped water supply systems. The problem in Addis Ababa is quite similar to a number of countries across sub-Saharan Africa. So I think many will get some insight how isotope hydrology can be used, not only to evaluate groundwater dynamics and surface water dynamics, but also it can be used on, in water management practices. We have also learned that with simple tracers, in a cost-effective way, we can use water quality monitoring, not only in groundwater systems, but also in piped water systems. So I think I can say it is an eye-opener for many of us to continue such a research in a cost-effective way. I'm sure you will continue because one of the questions raised in this session is that to relate this research with leakage and also issues of residence time and how the piped water moves from one point to another and changes spatially and temporally. So a lot can be gained from this work. Hopefully, Professor Seifu will continue working with us also, with many who are interested to continue in the same direction. In general, isotope hydrology was used in classical hydrology to understand hydrodynamics in subsurface waters and also, of course, in climatology. But now we understand that it can be also used in water management practices. I really appreciate that monitoring water quality is not a common ground across Africa. So even intermittent water quality monitoring systems can tell us a lot about the dynamics. So I really appreciate. We will work together. Professor Seifu will work also with the center. We really appreciate. Maybe I invite Dr. Fallaka if you have something to say. Otherwise, we can say goodbye and thank you.
Thank you, our moderator, Professor Enale Mayano. For those of you who are not familiar with Professor Enale, is a renowned hydrogeologist at Addis Ababa University. And I would like to thank Professor Seifu, who recently moved to the University of KwaZulu-Natal. So I hope he will be back to join us again. So still we are connected thanks to the technology. Yeah, so hopefully we will see each other in the near future for research as well as for teaching, student supervision as well. So I would like to thank the audience. We have more than 40 participants. So it seems this is a summer vacation in many parts of the world. So we may resume our webinar after end of summer vacation because we have relatively lower participants, especially from the West. So anyways, thank you very much. Great for having you. Thank you very much to Professor Seifu. Thank you all of our audience. see you during our next webinar after 2 months. Thank you very much.
Thank you. Thank you.
Thank you, everyone. Thank you. Thank you.